Hi, welcome back. This is Professor Ridge, and today's lesson's section 2.2 on functions. So we'll start off with definition of a function. A function is a correspondence between a first set, called the domain, and a second set called the range, such that each member of the domain corresponds to exactly one member of the range. Okay, so basically, if we have these two sets, say we have some numbers in here. The first set we call a domain. Second set's the range. And we're going to describe a relationship between these two sets and how we're going to assign the pairing between these two sets. That's a correspondence. So if I say, okay, 1's going to get matched with 4, 2 is going to get matched with 5, 3 will get matched with 6. This relationship would describe a function because each item in the domain, 1, 2, and 3, all get assigned one thing in the range, 4, 5, and 6. Okay, so this is a function. Okay, so let's try a couple examples. So determine whether each correspondence is a function. So if I'm going to say domain 1, 2, 3, 4, okay, so 1's getting paired with 4, 2's getting paired with 4, 3's getting paired with 4. So the question is, does this relationship or correspondence describe a function? Is it a function? And the answer would be yes. Since each element in the domain gets matched to exactly one element in the range. Okay, so it doesn't matter that the range only has one thing in it and all three, 1, 2, and 3, are each getting paired with 4. The idea is we don't care what's happening in the range, we're just looking at the domain. Each element in the domain, 1, 2, and 3, get paired with exactly one thing in the range. They all happen to go to 4, but that doesn't matter. So that's yes. Let's try another one. Say 4, 6, 8. 2, 3, 7, 9. So let's say 4 goes to 2, 6 goes to 3, 8 gets 7, and 9 is a partner. So this one would be no, since 8, which is in the domain, gets matched with 2 elements in the range. Okay, so that makes it no. Okay, another way we can represent a relation between two sets is using sets of ordered pairs. So if I have 5, 3, 2, 7, 4, 1, okay, determine the domain. So the domain is the elements that are in the first set. When you see it as a set of ordered pairs, the domain would be just the x values. So the domain would be 5, 2, and 4. Okay, so the range would be the y values, so it would be 3, 7, 1, or the set of second elements. Okay, and then is this a function? And the answer is, okay, so again, we're going to look, does each element in the domain, 5, does it get assigned just one partner? And yes, it just gets the 3, 2 gets 7, 4 gets 1. There's no repeat, so I'm looking for a repeat in the x's, and there isn't any. So that's, yes, it's a function. Okay, let's try another one of those. So if I add 2, 1, 3, 8, 4, 9, 3, 6, domain would be, again, it's just the x elements, 2, 3, 4, and then you don't have to write a repeat, so 2, 3, 4. And then the range would be the y's, 1, 8, 9, and 6. And normally I'd put it in order, so 6, 8, 9, but that's not required. And then is this a function? And the answer is no, since 3 gets paired with 2 y elements. Okay, so that brings me to alternate definition of function. So the way I think of it is each x's are the domain, each x element gets matched or paired with exactly 1 y. So every x gets 1 y, exactly 1. That's the key word. And remember, domain is the set of all x's, in range, set of all y's. Okay. But they don't have to be X or Y's, but that's typically the way we think of it as ordered pairs. Now, since I can represent a function as a set of ordered pairs, I can also think of it as a graph. So I can look at a graph. And we can look at this point, this point. So this first point would have been 1, 2, 2, negative 1, negative 3, 1. And looking at the by looking at the function, that this is a function, so I could say the function would be the set of ordered pairs negative 3, 1, 1, 2, and 2, negative 1. Domain would be, you can think of it too if you think of graphs, so it's all these x values. So it's going to be this point here, this point. So it's going to be negative 3, 1, 2, and then the range. So if I didn't write it as a set of ordered pairs, I just look at the graph. The range is the y values, so I take this one, this one, this one. So I'm going to get negative 1, 1, 2. Okay, so I've drawn a picture of a graph here. This graph represents a function. And so looking at the picture, I can determine what the domain is. And remember, the domain is the set of all the x values. So basically the way I think of it is if I can smush this down onto the x-axis, where is it going to hit on the x-axis? So you're going to look for the furthest point to the left, which is negative 4, furthest point to the right, which is positive 4, if I'm just looking left to right. And again, if you can imagine just squishing this onto the x-axis, all these points would be hit. So basically the domain is going to be the set of all x values, which will be from negative 4 to 4. Now the range, the range is a set of all y values, so I'm going to look for the highest point, which is right here at 2, 3, and the lowest point, which is down here at negative 3, negative 3, negative 2. And now think of it, if I were to squish this, push it against the y-axis, where would it hit? And it would be all these points between negative 2 and 3. So that's your range. So your range will be the set of all y's such that y is between negative 2 and 3. So that's the way you would determine it by looking at a graph. Okay, I can ask questions like, what's the range element that's paired with the domain element 0. So remember, the domain element is the x's, so if x is 0, go to the x-axis. Here's the point or the graph. So that's the point 0, 2. So the range element would be 2. 2 is paired with 0. I can switch it around and say what's the domain element. That's paired with the range element. Zero. So the range element is the y value. Right? So y value is here on the x-axis. So I can see that this point is -1, 0. So the x-coordinate or the domain element that's paired with y is 0, or the range element, is -1. So the vertical line test is a way that we can look at a graph and quickly decide if it's a function or not a function. And the vertical line test says if it's possible for a vertical line to cross a graph more than once, then the graph is not a function. So let's take a look at a few examples. So the question is is A a function? So what I got to do is imagine sweeping across every vertical line, so that this is one vertical line. Here's another vertical line, another one. Will any one of these vertical lines hit the graph more than once? And if the answer is no, then it is a function. If any one vertical line hits the graph more than once, then it's not a function. So this one will pass the vertical line test, and you'll say yes, it's a function. I had a graph that looked like this. And then the answer for this would be no, because here's a vertical line that has 1, 2, 3 intersection points with the graph. So it's not a function. So you just have to show one line hits more than once, then it's not a function. So that's all you're looking for. So it's a real quick and easy way. And the reason the vertical line test works is that one vertical line represents an x value. This is one particular x value. And for this, so say this was x equals, say 2. For x equals 2, it's getting 1, 2, 3 y values assigned to it. So this x value has more than one y value, so it's not a function. Okay, so again, a vertical line represents one single x value. Like in this case, x equals 2. So over here might be x equals -5 or -3 or whatever. X equals -3. And you can see this x value just gets one y value. Now, so what we're looking for is one x value that gets more than one, so it hits the graph more than once. And if that happens for any one x value, any one vertical line, then it's not a function. Okay, so function notation and equations. This symbol is red. F of x. Or you can say f at x. It's more commonly say f of x. It means the y value, this is the long-winded version, the y value for the function f so f is the name of the function. The y value for the function f given an x value. So it's describing how you match up y values. So f of x is a y value that goes with that x value. Okay, so f of 1 would mean, the long-winded version, it's the y value for f, or that gets paired, right? Gets paired with x equals 1. So it's the y value for the function f. Excuse me, I'm coming down with a cold or something. So it means the y value for the function f given x equals 1. So it's the y value that's matched with the x value 1. So if I describe f to be this function, 1, 2, 3, 4, 5, 6, then f of 1 is going to be 2, because it's the y value that gets paired with x equals 1. F of 3 will be 4. And obviously, f of 5 would be 6. So this is a y value when x equals 1, which is 2. Okay, so we can also define a function instead of as a set of ordered pairs like I did there. We can use this notation and give a function rule, an equation, to say what you need to do to x to get the corresponding y value. So in this case, f of x equals 2x plus 5. So once you determine what x is, you're going to multiply it by 2, and then you're going to add 5. So if this was the function rule, then f of 1, so I could say evaluate or find the function value. F of 1 would be 2 times 1 plus 5. So you take the x out and replace it with 1. And then do the math. So that's going to be 2 plus 5, which is 7. So f of 3 would be 2, take the x out, put in whatever's inside the parentheses for the x. So 2 times 3. There you go. So this notation allows me to define a few different functions. So I can say, so here, let me give you an example. So I can say let f of x be 2x plus 5. We'll stick with that. G of x be x squared minus 1. And h of x be equal to about 5x plus or minus 7 divided by 2. So if I asked you to evaluate or find the following function values, So if I asked you to find f of 3, just like we did up here, well, we did 3 already, let's do 8. So 2 times 8 plus 5 would be 16 plus 5, which is 21. If I asked you to find h of 1, now again, this h is the name of the function. This is the x value that you're going to substitute in for the x value, sorry. So we're going to put in 1 into the h function. So the h function is 5 times whatever your x is, minus 7 divided by 2. Now this is a good technique. Wherever the x is, you just leave it blank and put a parenthesis there. Then whatever's inside the parenthesis here, h of 1, you put it in the parenthesis. You're going to put it for everywhere you see an x. So now we do the math. 5 minus 7 is negative 2. Negative 2 divided by 2 is negative 1. So h of 1 is negative 1. And then g of, say, 3, let's say negative 3. So this is going to be x squared minus 1 is g. Inside the parentheses, I'm going to put negative 3. And remember, if it's negative 3 in the parentheses, you're going to square negative 3. So it's negative 3 times negative 3, which is 9, minus 1 is 8. Okay, so that's function notation. All right, the last thing I want to talk to you about is how do you find the domain of a function if you're just given the function rule and you don't have the graph, it's not written out as a set of ordered pairs. And so basically there's just a couple things that you look for. So this is number 62 in the exercise set. So the couple things you look for is basically if you're told it's a function, you know that the domain is going to be anything, it's going to be all real numbers, that's the default, you start there, and then you look for any values that if you plug in for x would make the function undefined, and then you throw those out. So the things that make functions undefined, as we look at this, we know that if you have 7 divided by 0, that's undefined. So what you have to do is restrict your domain to not allow this to happen. So the next question is, well, when is 6 minus x equal to 0? Well, it just says, just solve that. So you're going to add x to both sides. So if x is 0, then this expression, 6 minus x is equal to, if x is 6, then this expression, 6 minus x would be equal to 0. So we're going to restrict the domain Okay, so you're going to restrict the domain to not allow for x to be equal to 6. So basically, and again, the reason is if you plug in 6, you're going to get 7 over 6 minus 6, which is 7 over 0, which is undefined. So that x element of 6 would not get a y element because it's undefined. So for it to be a function, every x has to have a y. So the trick is, well, if you get an x element that doesn't have a y, you throw it out of the domain and then you don't have to worry about it. Okay, so our domain is going to be the set of all x's such that x is a real number. So it can be any real number except, so we write and x cannot equal 6. So basically anything else is okay. So everything but 6. And that's it. So Mainly right now all you're looking for is anything that would make a denominator 0. Like number 64, we have g of x equals x squared plus 3, and the domain's going to be, now, is there anything that I plug in for x that when I plug it in it's not going to give me a number as a result? So right now the only thing we're looking for is if you have a fraction like number 62 where the denominator is going to be 0, you throw it out. Well, that's not going to happen. No matter what I put in for x, I can square it and add 3 to it. So I'm going to get an output value. I'm going to get a y value. So the domain's the set of all real numbers. And the other thing we look for, which you don't have, it doesn't look like you have any here in this set, but the other thing, so the two things you look for right now is what makes the denominator 0, and then the other thing to look for is square roots. This it has to be positive or 0. The radicand, this number can't be negative. So we'll talk about that later when we get some examples. But typically you look for, if it's the domain, you just start with, it's going to be all real numbers, and then you look for anything that if you plug it in, it's going to make it undefined. So those things that make functions undefined are if you get a 0 in the denominator, fraction, or if you get a negative under a square root symbol. So right now, those are the only things we're looking for. And as we go on later, we'll discuss it some more. Okay, so that concludes lesson 2.2. Go to My Math Lab and complete the exercises there. See you next time.